We are continuing from our last video to look at approximating a definite integral. So in our last video we looked at left and right Riemann sums. We're trying to approximate the integral of from 0 to 2 of x to the fifth. So the integral from 0 to 2 of x to the fifth dx. And that's this area right here. Now we did that approximation with right Riemann sums, find the area of 4 rectangles. So we did an r sub 4, which is the sum of f of x sub k times delta x from k equals 1 to n. We worked that out. We also did a left Riemann sum here. So how can we improve this? Well, and what do we know about these integrals, about these approximations to the integral? Well, since this function is increasing, we know the left side is always going to be lower, the lowest point on the curve, so the left Riemann sum is going to be too small, or going to be smaller than the actual integral. The integral is going to be larger than this, and the right Riemann sum is too big. If the function were decreasing, this would be exactly backwards. When would they be perfect? Well, if the graph actually looked like a horizontal line all the way across, or at least on each piece was a horizontal line, then the left and right Riemann sums would both be the same, and they would be perfectly the same as the actual integral. So if the function were constant function, the right and left Riemann sums would be perfect, or even if it was just constant on each interval. But on a particular interval, if it's increasing, the right Riemann sum is too large and the left is too small. But if the function is decreasing, then the right Riemann sum is too small and the left is too large. And the thing that I want you to notice is right here, when you're looking at these two things here, this is something that is good news for us. The fact that one is too large when the other one's too small, no matter whether the function is increasing or decreasing. That tells us that if we average the two, we should get a better estimate than either the left or the right estimate. For reasons we're going to call this later, you'll see why we call it in just a few minutes, why we call this the trapezoid rule. We're going to call this estimate t, which is just the average of the left and right. Now how can we do that? Well, let's see, the left estimate we figured out was 4.3125. The right was 20.3125. And we just take those two numbers there, add them up, divide by 2. That will give you a number exactly halfway between that. So this is an area of a rectangle who, well, it could have the same width and exactly halfway between on the heights. And that's what we're going to see that here. So here's another function, and let's take a look at that. So this is a function which is decreasing on the piece that we're looking at. And so we're going to talk about just one rectangle here. This might be one of our little subdivisions. So the red one is a left Riemann sum, or left estimate, the area of that rectangle, and the area of the blue rectangle is a right one. So notice that the blue is too small, the red's too big. If we average these two, we get a rectangle whose base is the same as this, but whose height is halfway in between. So if I put these sort of together here, down here we put the blue rectangle at the bottom, so here's the height right here, and we get a rectangle down here below it, and the height all the way up the top is the top of the red rectangle. If we go halfway between, we're just drawing the height of the rectangle halfway between the blue height and the red height, so that if we draw that, this distance from this top part down to this midway point here to here, midway vertically, and then we do the same thing on the other side. So all four of these little segments, this one, this one, this one, and this one, are the same length. And so then we draw that rectangle, which is a purple rectangle here, and I've separated it out here on the side. So let's see if I can get where we can see all these at the same time. So we can see that we've got the red rectangle is the left, the blue is the right, and halfway between is the T rectangle. And so we can see the T estimate as a rectangle, the area of a rectangle, which is half as big, half as tall as the left, not half as tall, halfway between the heights of the left and the right Riemann sums. Okay, and of course we could do this on all the different intervals, not just on one. Now, why do we call this a trapezoidal rule? Well, let me show you something right here. Let's zoom in on this a little bit more closely here. So again, this is our second function we were looking at, which I didn't tell you the formula for. Well, actually there's the formula in the corner there if you can read that. But let's zoom in on this a bit. So here's our purple rectangle. Well, I want to draw a line segment, which is a secant line segment to the curve, and it's going to go to this point on the curve right above A, that point A, F of A comma, F of A, to this point on the curve right above B, B comma, F of B. So we connect those 2 points with a line segment. Now let's look at, do you see these two little triangles that are formed here? Well, first of all, because these are vertical lines and this is a horizontal top to this rectangle, those two things are right angles right there. Furthermore, these are straight sides across. This is a part of a line going straight across. This is a part of a line going here, secant line this way, horizontal line here. When two lines meet at a single point, these angles that are across here are called vertical angles, and they are congruent, meaning they have the same measure. Furthermore, by the way we drew it, we know that this distance from the top point down here to the top of the rectangle, and from the right point to the rectangle, those two distances are the same length. So those sides are congruent. So if you look, we have angle, angle, side of those two triangles congruent. If you remember from your geometry class, that tells you that that's enough to make those two triangles congruent. So among other things, what that tells us is that they have the same area. So if I cut off this little purple triangle right here and sort of rotate it around and put it right up there on that one, I would end up with the same area. What would that area look like? Well, the original area was a rectangle here, and the new area is a trapezoid, actually a right trapezoid. Right angles down here at the bottom. So the area of this right trapezoid is the same as the area of this rectangle. Where was the rectangle chosen? It was chosen so the height was halfway between the height on the left end and the height on the right end. So it was exactly the average of the left and right estimates for that one rectangle. And if we do this for each interval, we can see the left and right estimates average together to give us the t estimate, which is a rectangular area. But it can also be seen as a trapezoidal area, and so that's why we use the letter T for it. This is called the trapezoid rule estimate. So what are we essentially doing? Well, if we did a left or right Riemann sum, we're essentially assuming the function was constant throughout. If we're doing a trapezoid estimate, we might as well assume the function was linear, because it will be perfect if this is at a straight line here. Okay? In this particular case, the trapezoid rule is a little bit smaller than the area on that particular one interval, but we get the top of it there. So that is a trapezoid rule estimate. So we can visualize it not only as rectangles, which we certainly can do, but we can also visualize it as trapezoids. Okay, and so we approximated that to be 12.3125, and so we can actually illustrate that as the area of several trapezoids. Actually, we were using Graphmatica with this before. Graphmatica works for this as well. I can select trapezoid rule 4. Rather than drawing it as the heights of rectangles with the height being halfway between left and right, it's going to actually draw it as trapezoids, right trapezoids. So here we have a right trapezoid, here's another one, here's another one. Actually, the one on the very end, we can't really see it here, it actually degenerates down to actually a right triangle rather than a right trapezoid, because one end of it is at 0 on the x-axis. So we always get, well, either right triangles or right trapezoids, normally right trapezoids is what we get. So we get a bunch of trapezoid areas that we can put it together. We'll come back in our next video and try another way of approximating the integral.